Now let's talk specifics about these greenhouse gases. We've talked about the fact that the Earth's surface is a black body, and the Earth's atmosphere is not a perfect black body because of these greenhouse gases. But we haven't delved into the specifics of what's going on with those greenhouse gases, and it's time to do that. So in looking at this is a rather complicated slide that I'll try to make easy. What this slide shows is the spectrum of the Earth system's absorption of the sun's emissions. So the sun is emitting all along this wavelength spectrum in nanometers. And in fact, the sun emits over every wavelength, but these are the most prevalent in the sun's emissions. And in fact, the sun peaks at its emissions of the visible wavelengths that are right in here. What you're looking at is the Earth's absorption of those wavelengths, and in tan is the level in percent of the Earth's absorption of those wavelengths by either the Earth's atmosphere or by clouds. And you can see here that there's a big chunk that the Earth is absorbing 100% of, and it happens to fall into most of the UV range. And so the Earth's atmosphere protects our lives by absorbing so much of the very powerful UV energy that would change the DNA makeup of our skin and cause skin cancer, and change the makeup of interior organs as well, causing further cancers. These fall into UVA, UVB, UVC. We don't cover the entire amount of UV in the Earth's atmosphere with absorption. There is some left in here, this white area in here, and so that's why we wear sunscreen. In other areas, you see that there's not very much absorption in the visible wavelengths, which is why our eyes are evolutionarily adapted to see beautiful colors and to protect us with that sight. And then you see quite a bit of absorption in this area, which is in the infrared, and especially in this area, which is in the far infrared. So this is total atmospheric absorption. Here is the atmospheric window for visible light rays. Here is the atmospheric window for infrared Earth emissions. It acts as the vent to vent off the Earth's absorbed heat. So we have two atmospheric windows here. Now, to talk about the greenhouse effect of the gases that make up the greenhouse effect, we have a number of those gases that you know of. O2 is oxygen. O3 is ozone. The two of them, high in the stratosphere, do most of the absorption of the UV rays. High in the stratosphere. There is not very much absorption, but it is by O2, but it is very effective. There is a lot of absorption by O3, and that is life-changing. The ozone layer in the stratosphere basically saves life on Earth. Then in here, in the near infrared, water does an enormous amount of absorption of near infrared waves. And a little bit farther out in the infrared, CO2 does a lot of absorbing of infrared waves. The part of the atmospheric window that does absorb infrared and bounce it like a ping pong back to the Earth's surface is ozone that is lower in the atmosphere, like smog. Smog is made up of ozone. So there is some infrared that is absorbed in the atmospheric window, and that is related to ozone that is lower in the atmosphere. Then you see in the far infrared the impact of water vapor and carbon dioxide together. So all told, water vapor makes up 60% of the greenhouse impact of emitting infrared back down to the Earth. And carbon dioxide makes up 26% of that impact. The rest of these molecules, the oxygen, the ozone, and including methane, together make up about 14% of that impact. We talk about carbon dioxide emissions because that is something that humans can control. We can't really control water evaporation and water as a greenhouse gas because we can't control evaporation off the oceans. But certainly, if our climate change involves an increase in temperature, that's going to result in more water vapor, which is just going to heighten the impact that water vapor has on the greenhouse effect. So while water vapor is the real elephant in the room, carbon dioxide is what humans can impact. Let's look a little bit more deeply into that. This down here is the exact same spectrum that you were just looking at. You were looking at total absorption of many of the UV wavelengths, significant absorption of near IR wavelengths. You were looking at the atmospheric window for IR emissions from Earth's surface and from Earth's atmosphere with some ozone in there as absorbing some and ping-ponging it back. And then you were looking at water and CO2 as absorbing so much of the far IR spectrum of the sun's emissions. Now, let's look at these individually. We have here carbon dioxide. We have here the profile of water vapor and of molecular oxygen and ozone, methane here, and nitrous oxide, which also helps to make up smog. What you're seeing here is that water absorbs a lot of the warmer IR. Here's the warmer IR in the shorter IR wavelengths in here. So water does a lot of absorbing of shorter IR, and of course shorter wavelengths are warmer. Water also does a lot of absorbing in the far IR, which is cooler. Water vapor does 60% of the IR absorption as a greenhouse gas. And when we look at carbon dioxide specialty is really in absorbing far IR or cooler IR. So that the Earth emits in the moderate IR atmospheric window. And what happens when the Earth warms? Well, when the Earth warms, it will emit IR in a shorter or warmer side of the spectrum, more toward here. And as a result of that, that IR emissions from the Earth will get trapped by the water vapor that likes to absorb in that wavelength, right in the IR that is a bit warmer. So this is the sum of the specifics of greenhouse gases and the wavelengths that they absorb. When we look at the greenhouse effect, it is, as we said, absolutely critical to life on Earth, especially with the UV absorption by ozone and by molecular oxygen, and the ability of the Earth's surface to absorb visible incoming wavelengths. So that atmospheric window is part of the greenhouse effect and is critical to life on Earth. In addition, the atmosphere features those selective absorbers that absorb outgoing wavelengths of IR from the Earth and help to keep the Earth warmer. We couldn't live without water vapor and carbon dioxide and their emissions of infrared ping-ponging back down to the Earth's surface. Climate change, we know, is due to increases in some of these greenhouse gases that are related to human impact. And some of those greenhouse gases are carbon dioxide and methane and nitrous oxide. Methane is often associated with a lot of ranching and agricultural farming in terms of especially meat farming and cattle raising. So these are all molecules and compounds that are impacted by humans. And their increase can act to warm the atmosphere, and in warming the atmosphere, it leads to more evaporation. In more evaporation, more water vapor, that leads to more IR absorption and ping-ponging back down to the Earth's surface. So that warming can lead to more ice melt. Then, because there's more water, there's more evaporation. You see where this is going? More evaporation, more water vapor, more clouds. What do more clouds actually mean? More clouds, we don't know what it means. That's where this new science of atmospheric science needs your help, and it needs your study. Is this going to be a feedback loop that is positive, meaning that as the IR absorption increases with increasing greenhouse gases, we will have more water vapor and more clouds releasing more latent energy and warming the atmosphere even more? That would be a positive feedback mechanism, a circle that goes around that says more, 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 more. Or is it going to be a negative feedback cycle where more ice melt and more evaporation results in more water vapor and more clouds, but also results in more reflection of sunlight through thick clouds, and that reflection of sunlight will keep the Earth's surface cool? We don't know the answer to this. It really will depend on the height of the cloud formation from this increased water vapor. We know that high clouds, high thick clouds, will reflect more light and keep us cooler. But lower clouds that are thick will not be as efficient in reflecting and cooling. This needs a lot of research. One thing we do know is the sun heats the ground surface, and the ground surface conducts out to heat the top layer of air within the first few inches, and that is taken up by convection to move up and out into the atmosphere. We do know that the sun does not heat the atmosphere. The sun heats the ground surface conducts, then circulation convects, and circulation will heat the air. So you've been learning about the impact of the amount of solar radiation that is warming the ground. In terms of that, we know that the amount of circulation warming the ground will be greatest at the equator, because that's where the sun's rays are most direct. And so we will have a surplus of convected heat energy above the equator. But in circulating air around the globe, we can move it into the areas where there's a deficit of energy near the poles, 90 degrees north, 90 degrees south. And this circulation helps to keep that continuous, livable balance of energy on Earth. So latent energy and convection help to even the temperature around the globe by promoting circulation. And part of that circulation has to do with seasons, and you have seen or you will see a video on seasons as well. Thanks. Take care.